So last time we started by taking a look at some pattern recognition. In particular, we looked at a few kinds of sequences. The ones we spent most of our time on were sequences that were arithmetic and geometric. And arithmetic sequences are ones where you add to get every single term after it, right, in a recursive way. And geometric is where you multiply by a term to get the next term. So we're going to talk about a couple other things today after that. I mentioned, I can't remember if it was in this section, I think it was in this section at the beginning, this phrase, counterexample, before. So a counterexample is an example that shows something's false. That's what it really means. So it's a non-example, if you will. So this is a problem where a student has given you work. It's the basic setup. And the work for n plus 5 over 5 has been reduced to n plus 1. So they want you to find a counterexample, which means they're telling you it's a false statement. And they're wanting you to find an example that shows it's false. In other words, you've got to provide a numerical example. So what number could you let n be to prove that this is false? Lots of options, so pick one for me.
12.
Yeah, don't make it hard. 12. Thank you. N is 12. So if you have 12 plus 5 over 5, does that, I'll put a question mark, equal 12 plus 1? Certainly not, right? I mean, it's 17 over 5 on the left. That does not equal 13. Okay, so that's a counterexample to this particular conjecture. There's lots of n equals that would work here. In fact, most n equals will work here and show that this is false. But the student probably didn't think about certain values for n when they made this mistake. They were probably thinking about something else. So what reason do you think might have happened for a student to take this n plus 5 over 5 and somehow decide that that was equal to n plus 1? What did they do?
If they simplified it?
So they tried to simplify something. Yeah. What did you think they simplified, Abby?
By crossing out the 5s and saying that was 1. Because 5 over 5 is 1.
Yeah. I think you're right. I think that's a reasonable thing to think that they probably did. That would yield this idea of it being n plus 1 if that was what they were thinking. So we're going to write that out in words, all right? So you have your own words to say if you wish. I'll try to paraphrase what Abby said. So they may have reduced the 5 over 5 part to 1. So that's kind of what the problem is. The issue is, of course, why this doesn't work, but that fails to consider n divided by 5 as the other portion. Right, so this is really n over 5 plus 5 over 5. And the student forgot that both the n and the 5, I think this is at least likely what happened, forgot that the n and the 5 are both divided by 5. So that's a fairly common mistake. It's far more helpful to your students, it's far more helpful to you, if whoever's grading work is able to try and figure out what did you do wrong. Because if you can't figure out what you did wrong, then it's really hard to fix it if you have that sort of misconception in your mind. Well, I marked it out, I don't know why. Well, that's actually not very helpful to our students if we are not willing to take just a few minutes, maybe even just to recognize what might have happened to try to redirect thinking. All right, we're going to take a look at one other kind of numbers here that create patterns. These are fun ones. These are called figure-it numbers. And they're visually based on geometric patterns. Okay, so put the word visually in here because it's not geometric like arithmetic geometric that we did before. That's not what it's coming from. But geometric patterns visually. So there actually can be represented, this isn't the only way, but this is it is a common way to represent them by dots, arranged in certain types of geometric shapes. So triangular numbers is the first one I'm going to show you. And so I'm going to show you the pattern by showing you a few pieces of the pattern, right? So the first one is just a dot. The second one, you can start to see the triangle forming, right? There's 3 dots. The next one looks something like this. And I will do one more. So can you tell why they're called triangular numbers? The dots are in the shape of a triangle, right? Yeah, so we should be able to take this pattern and to actually continue it if we wished. Yes? Yeah. So what would we do if we wanted to do the next one? I'll change colors to indicate this is sort of our work now. What would we do if we wanted to do the next piece in the sequence? Okay, would I just add another dot on the bottom only? Okay, so that's one way to think of it. So Emily wants me to do something like this. Did anybody think of it in a different way? What did you think, Grace? That's another way to think about it. So you're adding another row on the bottom of it as a layer. So either one, you're going to achieve the same shape, though. Does that make sense? So there's not necessarily one always, guaranteed way that you should be thinking about it. But no matter what you end up with, you're ending up with now 5 dots on bottom and that same piece that we had from the previous step sort of stacked on top. I'd like for us to look at the numerical pattern that's present here. And what I mean by that is let's count the dots. What are the number of dots that are going on from one term to the next? So in the first one, of course, there's just 1. And then I have 3. So what's the next term? 6. And then, not quite, 10 first, and then 15, and then it'll go on from there. So these are the dots, the numbers. What I'd want to show you is that it's actually something we saw happen last time when I added a slide at the end. So I'm going to take those numbers, because I'm out of space here, and we're going to consider 1, 3, 6, 10, 15. And we're going to recognize first that it's not arithmetic, but there is a pattern. So this is adding 2, 3, 4, 5. And it kind of makes sense because as both Emily and Grace pointed out, you're either adding sort of this column on the left-hand side or right-hand side or the bottom, and it's 1 dot more than the previous one you had, right? So that sort of visually makes sense as well. But we saw this happen last time, and I told you that this had a name, because what happens if I do it one more time? What are all these? The same, right? So the name that we gave this last time, do you remember what I called these different?
The first differences.
Right, these are called first differences. It's just the subtraction or the amount you have to add to get to the following term, right? The first differences. And this one is the second differences. So this one actually has a common second difference when it's a triangular number. So now you see sort of a visual picture coming about that has the same patterning feature.
It's a triangular number.
So a triangular number is a number of dots that can be displayed in a shape that looks like a triangle.
Oh, okay.
That's it. So all my shapes here look like triangles.
So like 7, that couldn't be.
That couldn't be a triangular number. Correct. Yes, Sam?
So the whole 1, 3, 6 and the first and second differences, would that be the numerical pattern?
Yes. That's the numerical pattern that it's talking about here. The numerical pattern can be written as 1, 3, 6, 10, 15. So like my answer, I just wrote it above because I had more space. That actually is the numerical pattern that it's talking about there. Yes. So along that idea, Gracie, we're going to look at square numbers and notice the same thing. So triangular numbers form a triangular shape. And square numbers will have dots that form a square shape. So our square numbers, so the first one looks like, again, a single dot. And then I actually have 4 dots. Whoops, that wasn't very good. It's a little bit better. And then I have a little bit bigger square. And I'll do one more. So these are called square numbers because you can see the shape is square visually, right? So what's the numerical pattern that's created? I'll write it underneath the phrasing this time since I have a little more space. What's the first number of dots? 1. And then
4, 9, 16.
so can you imagine what the next one would be based on your maybe prior knowledge of these kinds of numbers? Emily? How many?
21.
You're close. 25. Because they're squares. So we have an idea too of calling these squared numbers because we can take the number like this is 1 squared, 2 squared, 3 squared, 4 squared, right? Again, it's not the same as an arithmetic or a geometric pattern, but there is a pattern present there. Not only that, but I have space enough on this screen to actually show it here, is that I can do the same thing I did a moment ago, where I look at adding to see to get to next number. I'll do one more number just because I think it will give me a little bit more data. So I add 3 here. I add 5. I add 7. I add 9. First differences are not common, but what happens when I do the second differences? They're all plus 2, you bet. So all these have a common second difference. Just like from the previous one that happened to. So this idea of these second differences comes about in yet another, sort of location. All right, so this is like forever ago now, 2011. I don't even know where you guys were in 2011. I don't really want to know. I'm starting to feel old these days. 5th grade, is that what you just said? 5th grade. It's wonderful. 5th grade. Well, I was here on campus. So that year, we've had recent changes in the structure of the university, so I probably need to adjust the description of this, but it's still a true statement. In the fall of 2011, we created a college on campus called the College of Math and Science, or Science and Math if you think that the sciences are more important. I like to put math first, just saying. So the Curley College was formed, and our dean at that time, her name was Debbie Blue, and Dr. Blue actually wrote on the board these numbers, 3, and then there was a decimal point, then it was 1, 4, and 1, 5. And she asked us to find the next 2 terms in the sequence of numbers. So I'd like for you to give your best guess of what the next 2 numbers should be as you look at those values. And why do you think those would be the numbers? So take a minute, don't talk to anybody around you. Just write down what your guess would be and why.
Is this if we had any prior math knowledge?
You would be presented this question much like I was. I walked into the room, this was on the board, and she said, find the next 2 numbers. That's all I'm going to say. What do you think the next 2 numbers would be? All right, without explaining your reasoning, I need one person to tell me what you wrote down. One volunteer. Gracie, you and one volunteer?
9,
9-2. Did anybody write down anything different? 1-6. Any other things people wrote down? Okay, so this is the two answers that people usually come up with. Some of you are looking at it and you understand why there are two answers, and some of you go, I don't know what that answer even came from. Can you guess what every single person in that room in this scenario wrote down? 9-2. Every single person in that room. Okay, so if you saw the 1-6, what you did was what? How did you get a 1-6? There's not a right or a wrong answer, by the way. What did you do to get a 1-6?
Just increase the value of like the second number after one.
Yeah, so it looks like it's going 1-4, 1-5, 1-6, 1-7, and we would keep going, right? Yeah, that's one way to do it. If you wrote down 9-2, how did you get 9-2? Because it's an expansion of the next two digits of pi. And who was in the room? Science and math professors. So that's where our minds went, right? Not because it's right or it's wrong, but because that's our reference point for seeing those values. We see those values and we naturally assume something. You, those of you who saw the 1-6, were thinking far more like the other patterns we've encountered so far in class, right? You were. So down here at the bottom, what does this tell you about inductive reasoning? Because that's what you just used. You used inductive reasoning to, based on what you were given, assume what comes next.
Using past experiences.
Past experiences, and what does it tell you happened based on the fact that you're using past experiences?
There could be multiple answers.
There could be multiple answers, right? There's not always, sometimes there is a right answer or a most natural answer, but there's not always going to be correct answers that come about, right? There may be multiple perspectives that taint what you do next. And in fact, it was very interesting because I will tell you in that room, everybody was like 9-2, and why is she asking us such a dumb question? I know that's what we were all thinking. This is what I was thinking. I was like, okay, what's the point? And that was just her point, is that our prior expectations, our prior experiences and so forth will taint how we see things, and that our students or other colleagues or whatever might not think of it the same way we do, and it's potentially at least equally valid. Okay, so inductive reasoning might end up with multiple different right possibilities. All right, so we are finished with 1.2. So we're going to get into groups and do group work now. You've got lots of times to do your group work. You should finish it. And then the homework for 1.2 will be due on Monday. Okay, Success Center is open and staffed for us on Sunday night if you need them. I do have office hours on Monday before then, too, if you need to come ask questions.